But over the last 30 or last 50 years, there are a lot of research on use the materials, how to use the high strength material or light alloys to reduce the weight of vehicles. This is, we can say, is a continuous job, and then we will have a big effects for the car body and the chassis structures. If we consider about use of materials, and we collected some data and made some predictions from 1977 to 2040. And we can say the the use of steel becomes less and less over the years, and aluminum should become a higher amount use aluminum, and the magnesium alloys keep the more or less constant. And we can see for the car body and the chassis structures, 80% will be metals, and the polymer and composite and will keep the fairly steady because it's too expensive to use for car body and chassis structures. And if we talk about steels, even if they are decreased over the years, and but steel has got a different kind of grade of steels. For low strength steel, that will deep drawing steel will become less and less, and will be minimized over the years. For the current high strength steel will be reduced as well. Third generation steel will increase, and the ultra high strength steel will increase because the materials becomes harder than difficult to manufacture. Okay, if you look at this diagram that shows the elongation, this is the relative strength of materials. That's the strength divided by the density. And we draw this horizontal line, and which is about 25%. Above this, probably the materials can be formed with use the stamping technology, cold stamping technologies, and it's fairly okay. But below this is very difficult. That we can see aluminum 6000 series, 7000 series, and like boron steel, that's ultra high strength steel, which are very difficult to form. We have to think about other way to do this. And to solve the problems, and what we do, and in the world, there is one technique has become popular. That's a steel called boron steel. They put some boron in the steel, the chemical elements, to change the CCT diagrams. But I'm not going to talk the material science here. And what I would like to say is that this is a very successful development for boron steels. Over 500 production lines are available in the world, and every production line can produce 1 million components in a year. And there are a lot of applications. And I'm not going to discuss the details about the technology, but basically, we increase the heat, the temperature for the material, and then we form it, use the cold die quenching to get martensite, get very high strength of material. But this have a lot of advantages, and ultra high strength, and get save the material in the meantime get the components lighter. But the activity is lower for this with the high temperature, the cost, the energy, and the various kind of other issues comes out. Then, but even though, because the global requirements for CO2 emissions, and what we do here, and can reduce the weight, then save energy. For example, Volvo has been used this significantly over the years, and currently 29% of components on the Rover on XC60 generation 2 has been they use the hot stamping technologies. Many use boron steels. This is the good achievements in China, and many places followed up as well. In China, over 200 production lines are available nowadays, and a lot of applications for this. And generally speaking, we say for these technologies, we increase temperature about 900 degrees C, get the steel into the austenite state, then we form it in cold die, we do the quenching. But I'm not going to give more detailed technologies. If anybody interested in this, you can look at our papers published, and we published many papers over the years on this. But 900 degrees C, we think this is too high the temperature, and oxidization, surface problems, and so on. Then we try to develop new alloys, and which can reduce the austenization temperature by 150 to 200 degrees C, and this we call it low temperature hot stamping. Now, again, we published some preliminary work, but has not been used in the industry yet. But we have showed the advantages of this. We can avoid this coating various other issues, increase the productivity significantly. Another techniques, and I mentioned this is boron steel. We have to use hot stamping, and new third generation steels, we need to use hot stamping to do this. And for aluminum alloys, there is particular features of the alloy is very difficult to form. Then we develop a technique called HFQ technology, to HFQ to form the part, and this is the trademark registered by our spin-off company. I'm a founding director of the company, and you can see we patented the technology over many countries, including all the countries in Europe and Asia, many places in Asia, Japan, etc., and manufactured many components. And for this one, we has been used on car body and chassis structures. The first one used for Aston Martin BD11, and now 24 components are manufactured using the technologies. And Lotus, door inners, and Lotus is the first company use our technology. Now Lotus is controlled by Geely in China. And for aircraft applications, and this is the armrest for aircraft seat. And many parts has been manufactured. But when we design a manufacturing process, especially hot stamping, is not very easy. And what we need to do is a basic test is a uniaxial tensile test. We need to generate data. We know the properties. Then we can do the simulations. And then another data we need to generate is the forming limit, because it's a sheet metal. And we say this is a minor strain, this is a vertical axis is a major strain. And for the if the curve, we say forming limit curves, if above this, that's failure, below this, that's safe. We need to do the similar to generate the data for these. But it's very difficult to generate for the data because it's new technology nowadays, and until we develop the technologies, nobody in the world can generate data to get the forming limit yet. And the reason is that, you see, the hot stamping process, I mentioned you increase temperature to a certain level to do the heat treatment for the material. Then you need to drop the temperature to a certain level with a controlled cooling rate. With the controlled cooling rates, then you do tensile whatever testing and get the data. But it's very difficult to control the cooling rate, and this is a problem. And how to do this? And but there are a lot of international standards available to do the uniaxial and the biaxial test, but it's very difficult to control the temperature profile required by the materials and by the industry process. That's the big issue. Then this forces us to develop something to generate the data. And what we do is we use a global material simulator. Probably people will know this. This is 3800, and it's the machine is developed in America and DSI, and we bought this and developed various kind of techniques based on these kind of facilities. And firstly, we generate, we create the specimens. Here is the tensile specimen and the biaxial specimen there. And we use the camera, we paint the specimen, use the camera, probably you heard about DRC's method, digital image correlation scheme, and to get these, to collect the data to work out the strain fields. But the problem is that when the material close to failure, the paint disappears or peeled off, then it's difficult to get the data at a later stage of the deformation. This is crucial. And now, previously, it's difficult to get 60% of the deformation, the data after that, and it's difficult to judge. Then we developed the cross-polarization method. We call it XPO method. XPO method to get reflections, get rid of these kind of problems, and to get the data. And here I give you examples. The results has been published recently. You can see 2024. And if we say this is the aluminum alloy AA6082, and without cross polarization, and when we get the data at a certain without this, we get the data about 70% of failure, we say start to peel off the paint. At 100% deformation, you can see the material, the paint has been peeled off. You can't get the data. But here, with the expolarization, we get nearly failure. For example, 80%, 98% of deformation, we still get good data. For the biaxial testing, and we look at areas with over 60% of deformation, the peel of the paint starts, and because the paint is very brittle, it's difficult to contain to stay on. We tried various kind of painting techniques, and eventually it's difficult to solve this. But with 90%, you can see 90% of deformation, and a lot of paint already disappeared. And with the cross polarization, and you can see we can get the data almost close to failure. And if anybody interested in this for strain measurement, use the DIC, you can look at this paper to get the detailed technique. Okay, then we do the uniaxial tensile test. For uniaxial tensile test, previously we mentioned about we need to control the cooling rates. This is very important. The Glebo can do this very well. And then we use the Glebo to do this kind of work. And we use the polarization method to get the strain fields and so on. But you can see this is the specimen from the center of the specimen. This is the major strain. And if you look at across these areas, the strain is not uniform. The strain is not uniform because of the temperature gradients. But we published a lot of papers, a lot of research on how to control the temperatures. And I'm not going to discuss this today. If we look at the strain rates, for example, at this L1 location, the strain rates is like this, increase like this. If you look at L3, the strain rate is like this. At high temperatures, we know the strain rates is very important to get the data, get accurate data. And our challenge is how to apply the appropriate, proper displacement so that the maximum strain rate within the specimens equal to the target strain rates. The target strain rates, for example, we put 0.5, which is very difficult to achieve, use traditional method. Then what we think, okay, we use previous data, we know this is not correct, but we do the learning. People say this artificial intelligence, whatever I say, just the machine learning, use data-driven experimental work. We generate previous data, we just input the data in, and then use the data, we try to find the characteristics of the data, how to process this and so on, present in proper ways. And then we do the training and the learning. Then we can set up this and go to stage 3. We can give a choice of this kind of what kind of learning method we choose, then generate data to control the displacement for the materials. At the end, through various previous data, and we generate the data, then we know the displacement and the time. We know this data. For any kind of test, if you give a target strain rates, then we generate this automatically for you, the system. Very simple. Just PhD students spend 6 months, but it's mathematics students are recruited. Spend 6 months to generate the job. Very easy. Then we can do the data to compare this. Previously, we can see for the conventional method, the true strain development is like this. If you say strain rates, target strain is 0.1, and we try to set 0.1, but previously the strain rate is like this. The error up to 1000%. The error is very high. And if we set the target strain rate 0.5, and conventionally it goes like this. But with this kind of a learning process, we can get more or less close to this. The error can be controlled within 15–20%. And it's difficult to get rid of the error, but compared to 1000%, this is a huge improvement. And what we really want is the strain data. For example, for the strain rate, target strain 0.1, and this is a true stress. This is horizontal is a true strain. Previously, when we get do the test, because the strain rates is not properly controlled, we get data like this, strain data. But with the proper control, we get data like this, which is significantly different from that one. For this one, for the strain rate 0.5 is similar features we've observed. And the flow stress error is about over 25%. The most important thing is for stamping, probably, for stamping, deep drawing, and this is the N value, the slope is N value. This is very important, but the real material properties has the N value is very, very low, very difficult to form. But the data we give, traditionally to give the data is something we say give you wrong indications for this, and can lead to the failure in real practice is not conservative ways. But I have to say, in the world, almost all the people work doing the generated data like this, but which is significantly wrong. And simple uniaxial tensor test need a lot of research. This generate proper basic data for your modeling. Okay, and we tried for different different materials, different strain rates, etc. Then we can say the blue is the real data, material data, and this color one is represented at its wrong conditions generated previously. Okay, then I move to biaxial testing for this. For biaxial testing, and people probably know this, there is the international standards, ISO 12004, and this is we call it Nakajima test, and available in the world for doing this. As I mentioned before, we have done this for various conditions for many years, but for hot stamping is difficult. The reason is that if we can't control the cooling rates, this is the problem. On Glebo machine, we can control the cooling rates, and this is a significant difference. That's why what we do is we use the Glebo material simulator, use the proper cooling facilities to control the cooling rates, then can generate data for this. And it's very simple. What we do is we generate, because for Glebo material simulator, only be able to do tensile test or compression test in uniaxial ways, but now we can do torsion as well, but could not do plane stress tension. Cannot do this. we designed this kind of a simple device attached on Glebo so that the 4 jaws here attached to this kind of specimen and can stretch the materials to perform in proper way. And this has been patented and with a planar test system and got a global international patent for this kind of device. And if anybody interested in this, you can see the paper we published on this. There are few parts what we need to consider for this kind of, sorry. A few parts what we need to consider, and one is the specimen design. For this specimen design, what we need to consider few criterions. One is we want in the gauge area, in the middle, the gauge area, we want uniform temperature, as uniform as possible. That's one thing. And another is for the strains, we want in the gauge area, we would like to have fairly uniform strains. And also, we want to failure initiate and occurs in the center areas. And that's what we try to do. But to ensure this is not easy. And we say simple biaxial testing is not easy to do. And also for the strains, we need to get linear strain paths. But if we want to get non-linear and path dependent, you should also be able to do this as well. Therefore, we design various types. We summarize with 3 types of design. I'm not going to discuss the details. And again, these technologies the specimen designs has been published in the Journal of Materials Processing Technology. And firstly, we look at temperatures, how to heat the materials, because for this kind of specimen non-regular geometries is very difficult to heat. And we developed a way how to heat this, check the temperatures at different locations. And then we look at the failure when we stretch the material. What's the strains for type 1, type 2, type 3? We can see type 3, the failure occurs almost near the center of the specimen, and type 1 is a bit away from this. And we also check the loading path as well. For uniaxial plane strain conditions, and we can see all failure occurs very close to the center areas for this. Therefore, for this kind of work, what we concluded in the previous paper I mentioned, the type 3 is a recommended specimen design. What we try to do is we try to create an international standard, including specimen design, testing procedures, and data processing conditions. And for this one, we try to compare with current international standard. As I mentioned, Nakajima test. That's the international standard developed in 1980s. That's standardized in 1980s, but which is not suitable for hot bending applications, as I mentioned before. We choose the material aluminium 5754, which is the almost the most ductile material, and for aluminum alloys, we generate different straining state and get data for this. And then we compare with the data we generated. If you see the key, the data, what we generated with our biaxial testing data, and which is more or less the same compared to our biaxial data, because in this way, and we can, sorry. Yes, in this way, people could believe the data you can generate, equivalent data can be generated at room temperature, at least in these conditions, because at hot stamping conditions, it would not be able to generate use Nakajima test to do this. And then we need to determine the onset of localized necking. If we stretch the material, probably people work on stamping, you know, one is the necking strain, one is the fracture strain. And the people are interested in this, how to determine the necking strain. We generate have the zone, fracture zone, and with the reference zone there. And if we plot, if it's uniform deformation, the thickness reductions would be linear. The ratio equals 1. This is the thickness reduction. This is a thickness reduction in the base zone. This is the reference zone, would be linear. But when the necking occurs, this becomes non-linear. It becomes bilinear. And we can find the intersection point, we say, define this is the localized necking. Again, for this one, we created a method we called spatio-temporal method to determine this kind of fracture and necking strain for the material. And I'm not going to discuss this, but we have done a lot of work at different conditions and to determine this and validated this is appropriate way compared to the conventional method for the same conditions. This has been done, and then now we can generate data. We can set up, we know the specimen design, we know the testing procedures, we know how to measure the strains, and also we need how to determine the necking strain and the fracture strain. That's all the data, and all the technique has been established. And for every part, we publish many papers to try to get the scientific understanding of the problems. And now we try to do the testing for boron steel, and which is commonly used for hot stamping. And this is a specimen, and we paint this, use the painting, and I'm not going to discuss this in details, and probably most of people know Glebo. And with the biaxial test rig, we developed, patented, and attached on Glebo. Then we did the test for this with different kind of temperatures and strain rates, temperature and strain rates, and with a different condition, we just show 3 near equal biaxial and near plane strain and near uniaxial tension. And we can see the failure occurs almost all of them in the closer to the center of the specimens, which is what we want. Okay, then we can use the method how to determine the necking strain and the fracture strain for different conditions. For different conditions, then we plot the diagrams. We set the forming limit diagrams with the fracture limit as well. And for different temperatures and different strain rates, for different temperature and strain rates for the boron steel. And once we get the data, then we can develop the equations for modeling. Again, for the forming limit diagrams and hot stamping conditions, we are recognized as the first one proposed the method in 2014 to model this kind of behaviors. And the method has been specifically applied to boron steel in 2022, and to generate this set of equations. This is a general viscoplastic constitutive equations, probably most people know because they come from engineering, I believe. And we introduced 2 damage parameters, omega-1, omega-2. One is to control the diffusing necking behavior of materials. Another one control the fracture of materials. And we put this into 2 steps. The first step is the uniaxial relationships for this. We can generate proper data for uniaxial tensile test, and then we can fit the data, fit the experimental data to determine the parameters like K, N1, and so on, the B in the constitutive equations. The method has been given in the book, my book, Fundamentals of Materials Modeling for Metal Processing Technologies. If some people have read this, I believe. And then second step is fitting for the forming limit and to determine the two damage parameters, and that can be done. And we do the various kind of analysis to see the generic features of these two equations. For example, if we change parameters within the equations, we can change the shape and so on. We know which one controls which, and then has got flexibilities to suitable for different kind of materials. Sorry. Yes, and that's finishing my presentation for the technical aspect. What we try to do is try to say the new material processing technologies need to be developed to meet the new global requirements. Because now CO2 emissions and forming light alloys, get lightweight structures, etc. There are many components I show in the last week in my presentation. Those are first time can be made, can be manufactured in the world, and before our technologies, nobody can manufacture those before, and with a low cost as well. Because of all these kind of new technology, we need to optimize these, we need to determine these, and we need to do computer simulations. We need good experimental data. Therefore, we need to generate, we need to advance the experimental science and the technologies. Therefore, we need to meet the new requirements for forming requirements. The next step is testing procedures need to be standardized. We still have not done this yet. And last time we ran a European project with 9 countries and 21 partners. We try to standardize this, but still have not achieved it because they need many laboratories over the world to test this and to verify this kind of technologies, which is challenging. However, in our division, we have generated over 10 international standards in the last 10 years, which is good. We do have track record working on this. Okay, thank you very much. And any questions?
Okay, this is the Q&A time. Any questions, any discussions you like to raise with LIN?
I have a question about your tensile test data. So you try to tell us that you get two curves, one is going up, one is almost flattened, and then you say that the flattened one should be the real data. But my question is because it's a tensile test. So if you get a flattened true stress, that means in the force transducer, you will get a reduction of the force. So that when you do tension, right? So the cross-section area is reducing. So that means you will get a reduction of the force. But can you show us some evidence of the reduction of the force? Because normally metal, we think that it can be hardened by plastic strain.
Yes, and it's a computation process for large deformation. One is the material could be hardened. Another is the cross-section area can be reduced. Generally speaking, the force reduces anyway. And for large deformation, the reduction of the cross-sectional area and the effects is larger compared to the dislocation hardening. Generally speaking, the force is reducing. But for this one, I show here is the true stress strain curve. Use the current cross-sectional area and the force, total force reduction, but the stress does not reduce very much and keeps more or less horizontal.
What's the initial cross-sectional area? I think it's called engineering stress, not true stress.
Yeah, if you use engineering stress for large deformation, then it would be like this. But for large deformation, people rarely use engineering stress, and more than 15% of the failure strength, people do not use engineering stress. But there are many definitions like Rangin strain and stress. Kirchhoff stress, and you can use different kind of stresses. But on metal forming, we mainly use the true stress.
to follow up this question, when you put, I got a mic. After you soak it for 60 seconds, and then you reach the temperature, and then you start forming. So at these, does the dislocation hardening effect be diminished due to the high temperature effect?
Okay. The main thing is for steel, for example, the initial structure is 30%, but I did not mention here, and generally speaking, it's 30% bainite, 70% of ferrite initial stage. And when we increase the temperature about 925 degrees C and keep it for 1 to 3 minutes and can be austenized, at that time the crystal structure changes and the materials becomes austenite state. The ductility becomes very high, and all dislocation densities, apart from the natural defects, that would disappear. But that's the reason that we try to reduce temperature very quickly, because we try to form the material within the austenite state. If we drop the temperature slowly, it will enter the bainite and the pearlite bainite regions. Then we form the part with, when we do the forming, the material is already bainite, and the ductility can be, the ductility of material decrease significantly. We try to form the material within the node, before the node of sickle. Sorry, I have not brought this. If you know the CCT diagrams, that's why they put boron in steel. Put boron, you can move the CCT curves to the right-hand side a bit, okay, so that required cooling rates is lower. And currently, the minimum cooling rate is 24 degrees per second. But what we need to do is with the consideration of dislocations, various things, and the forming process, we need to decrease control the cooling rates about 50 or 60 degrees per second, so that we have time to do the deformation. If we do the deformation too long, and we will enter the C curve, and the material becomes bainite or pearlite. That makes something when the data is not valid anymore. It's a bit complex for this. We need to control the phases of material.
You try to form it still in austenite.
Yes, that's right. When the material need to be formed in austenite state, so that we can get a maximum ductility of material, and also get the flow strength is low. Flow strength, that forming force is low. And that's the key aspect. For aluminium, slightly different mechanisms. That's a solution heat-treated material. We need to get a fully solution heat-treated state to enable the part to be formed.
So you need a longer soaking time?
Not so. Yes, if the C curves move to the right-hand side, that's better. But sometimes it's difficult. Yes.
In the real production process, just in your experiment, use air jet to do the cooling.
Correct.
Okay, you control 25 degrees per second cooling rate.
Okay, we have got
real production process. What exactly the media used to
okay.
cooling
rate? In the real manufacturing process, we just monitor the cooling rates of material. The minimum cooling rates of material is above the critical cooling rates. That's it. We only model this, and we can't get, because different locations has got different cooling rates. Because the cold die contact some areas, cooling very quickly. Some areas have not been contacted to the die. The cooling rates is lower. We try to control the lowest cooling rates must be above the critical cooling rates. We only control that one.
Just one question. 9. Bernard Rofi asked, your fracture model appears to only consider linear shrink path. Do you have a non-zero linear shrink path approach as well?
Yes, and yes. Yeah, this is a good question. We only consider the linear straining paths. We have not considered the non-linear strain paths, different strain paths yet. And there are two reasons. One is we planned this to do this work, but has not been done yet. And secondly, we did a lot of tests for non-linear strain paths, but a linear strain path, we get the minimum activity of material, lowest fracture limit curves. That's the most conservative way to predict. If we can satisfy this and all other conditions would be okay.
Any more questions from online? Yes, please.
Hello, Professor Lin. Thank you very much for your great lecture. I have a simple question. I see there are many applications in the automobile industry, and now the new energy, new resources vehicle, such as new resources, new energy car development is very significant. Would you please give some comments about the application in the new energy vehicle, new energy car? Thank you.
Okay. Yes, we say new energy, and generally speaking, I do not use the term as an electric car or hydrogen car because it's not new energy. Electricity has been used for 200 years or something, and just use the car for over 100 years as well. But now I don't know why here I try to say new energy. And for full electric cars, I would consider there will be a future. But in any case, if you reduce the weight of vehicles, currently we did work with the automotive company, and if we use our technologies, reduce the weight, we can get the travel extension by 25%. That means if your car can drive 400 kilometers, but if you reduce the weight, use proper way, you can drive for 500 kilometers. That's the effects on this. But I think new energy and full electric cars will become so popular in certain regions. And technologies compete to each other. For example, in Europe, previously they promised do not produce fuel cars in 2030, but now extended for 5 years. And because 2030 is coming, then extend to 2035. But when reached to 2035, I don't know what's happening. And they compete to each other and use the electric car. That's the one issue. Another is hydrogen and use other gases, or people try to change the fuel as well. There are a lot of researchers and development in the subject area. But in certain regions, the electric cars will be, probably you mentioned about new energy, that's electric cars. Electric cars will be heavily used in certain regions, like in China, in south part, but not in the northeast or far northwest because it's too cold. The battery efficiency drops by at least 50%. Okay, I'm not sure if I answered your question, but just a discussion.
Yes. Professor Chen.
Oh, thank you very much for your very inspiring talk. Now, I'm a layman here. I'd like to ask a layman question. It's very good that you can reduce the weight by using this light material. And then, of course, if you use the same energy, the car will run further. But on the other hand, when the car weight is reduced, or do you worry about the stability of control of the car? Especially when you have like a gust of wind. When we drive in a highway, normally we feel the car is more or less flying. What is your view on that?
Yeah, okay, thank you very much. And this kind of things has the questions being argued, been asked many times because people consider about safety. And what we do is we did a lot of analysis in collaboration with the car designers and like Jaguar Land Rover and Lotus Lotus Engineering that design cars. And they consider about wind, for example, the size of the car and the wind. If you get a typhoon, for example, and probably turnover is too light. And that's one thing. Another is, according to the standards, is the turning angles. If you drive too fast and it's lighter, if you turn around, then probably roll over again for the car. But there is the international standards here, and we, according to the standards, we did an analysis for example, for currently I drive Toyota RV4, which is 2 tons. 2,000 kilograms. But according to this kind of analysis, 500 should be enough to meet the requirements. And because we have a long way to go to reach to 500 kilograms, then consider about this kind of conditions. This is for standards. But if you hate, if there is an impact between 2 cars, you drive, one is lightweight, another is heavier. The lightweight will sacrifice themselves and with danger. This is the reality. But with the international standards, and if everybody becomes lighter, and that's okay. If some cars are very heavy, very light, and if you hit on the truck, you would be in danger. For example, in US, F-150, that's the largest sold cars for this. The US government has got regulations. If over certain weight, you are not allowed on the road. That force them to reduce the weight, then use our technology. Probably depends on government policies. Otherwise, they will not use it. That do not bother. In America, the big cars, fuel is very cheap, pollution and something leave to next generation to consider, not now. I'm sorry, and this is the reality. And government policies are very important, like electric cars you mentioned. And without government policies in China to promote this, would not be able to develop to the current state.
Thank you very much.
I'm sorry, and the lightweight has problems.
Another online question. Professor Lin, your research group has won for its excellence in partnership. You also received 2021 ISME's Gold Medal Award for your contribution to UK metal industry. From your journey, what are some prerequisites for achieving successful technology transfer? What would be your advice for academics to step out and be more entrepreneurial? Any niche knowledge and skills they need to be equipped with questions, or to do with entrepreneurship?
Okay, thank you. This is a very big question, and I try to answer, try to give you my opinion on this instead of answering the question. And over the years, we did we received a lot of government funding, and also received a lot of industry fundings. The reason is that we do something very largely used in industry. For example, for car body and chassis structures, over 70% of components made using various kind of forming processes, because it's a large use for aircraft, for trains, and so on. There are a lot of applications. Therefore, for those kind of larger applications, and I think there are a lot of companies working on this as well. They have specific problems would like to solve. That's why we established 4 research centers for different companies, and the support from industries would be important, I think. And another thing is, for an academic research, we are not a consultancy company. We are not only to solve the problems for industry, not only. We try to solve the industry problems. In the meantime, we try to find scientific challenges. Without scientific challenges, for a project, I would not do. That's why we need to keep scientific challenges so that we solve, answer something related to science, then we can publish good papers in LIN international journals. So this is important for academics as well. That's why you need to combine with the scientific applications and so on. For example, we did, I did not mention here, and we have a technology called a flex-extrude. Is a deformed material with curved structures, extrusion then bend into a structure components. Initially, an aerospace company proposed this to me. They said they want very light and very thin walls, extruded component that bend into a structure. I did a simple analysis. I said, no, you can't bend because either cracking or buckling occurs. You cannot bend the material. But they said, I'll give you a lot of money and could you help us to do this? There are a lot of science, but I think the market is not huge for this. For aerospace, they're used for example, for sending satellites to the sky, etc. They do not use, the market is little. But after a couple of years, and the high-speed train company talked to me, they said a lot of bending, they have got designs and so on, but could not bend. I think the market becomes bigger, slightly bigger for trains and underground, etc. High-speed trains, underground, then market becomes slightly bigger. But when this motivated me to do some research on this. But I did I talked with the people from industry, from automotive companies. They said, for example, for Lotus cars, they said 29% of components could be used extrusion process, but difficult to bend. That's their problem. Okay. 20% of the car body structures could be used for this technology, plus aerospace, plus aircraft, etc. Then motivated me, and I think I need to do this. Then I organized a team and get government funding and so on, and to do the initial investment. Then started the work. Then eventually we created a new process on this, and that's the first one in the world. And now is a trademark as well, called flex-extrude technology. And this kind of things happening because what we try to do, consider about market, that's one thing. Another, for academics, we need to find the science behind. And for example, for that kind of technology, I talked to Professor Fu on this as well, because the material shear and the grain size become reduced by 200 times. That's increased strength. We did develop, understand mechanisms, and develop modeling method, etc. Lots of other things we need to do, understand the science, further optimize the process. But in my opinion, I do not encourage young academic staff, mentioned about academic staff, do not encourage young academic staff. Today I become a lecturer or assistant professor. Next day I try to set up big companies to do something. But probably affect your academic research. At universities, academic research, I think, is most important. And but put your research results in the for applications. That's another results. But not everybody can do both well. You need to judge yourself, what's your interest and so on. But initially, I would like to you concentrate, suggest to suggest you concentrate on scientific research and get good foundations. Then the later stage, you feel some technologies could be commercialized. But another advice is instead of step out from academics, I would suggest the people, for example, professor, you develop new technology, but it's not necessary you have got an ability to commercialize this. Need the proper people who do commercialization to do this. For example, in the UK, there are a lot of professional managers that help you to do this kind of things. And I found the director for 3 companies, but I do not run company. For first company, my contract with them is 3 hours per month. I just sit in the board and report what's the progress, give some support, and which done not 6 days per year, which does not affect my scientific research, because my strength is scientific research or solve technical problems, but it is not run a company. But in China, there I know many professors is researcher and company director, CEOs or president and so on, multi-jobs. They are much more clever, but I have not got such capabilities to do everything. Okay, that's my suggestion and advice.
Thank you. Right. For our young academics, we think before you get out, set up your own company.
Everybody tries to become a billionaire at the initial stage, but it's not realistic.
Yeah. Now that brings in another question that we have in Hong Kong about the IP ownership. In Hong Kong, we are always arguing with the company if they fund academic to do a certain research, get an IP. Who owns that IP? Always argue. What's the practice in the UK?
Okay, in the UK, it's the same. If the company sponsor certain kind of research and they will argue, they try at least they try to maximize their IP ownership for certain reasons, because they're paid for the research. But there are regulations. For example, if you apply the government funding like EPSRC and the Engineering Physical Research Council or European Commission, etc., the scientific research, and the college or university will own the IP. Anything happen with university will own IP. The funding agency do not own the IP. Therefore, for research, and many people ask me questions, why generate so many patents and special techniques. But I also collaborate with a wide range of companies and the setup centers, etc. How to manage this and to deal with this. It's difficult, but we are fairly successful. All the, we say, use the word useful IP or original IPs owned by us only, not for a company. For some applied, and it's not an original applied owned by a company, but we do not bother too much for this. We have to have a, sorry, and if I say this, and maybe in the future, the company would not like support me anymore. But that's the reality. You have to control somehow. And all our IPs have no argument with the companies. All companies work with me. I'm very generous. All IPs belong to them. They're very happy. Because there are some scholarships available. For example, university have some scholarships, and I have some extra money to support PhDs. And if I have my own ideas, try to do the original work, I try to let the students to do this alone, do not attach to any companies, to avoid this kind of IP issues. Very difficult, very valuable things need to be considered.
One more online question from England. Have you developed some tailored hot stamping models, which include different phase transformation of current steel?
Okay. Yeah, my understanding is that tailored hot stamping models. That means the different microstructure, different locations. Yes, we did some work on this. For example, for bumper, for automotive bumper front part, in the middle part, we try to get all martensite because we want stronger. For the end, 2 ends, try to get ferrite because get higher ductility of material, less how to say, less brittle, because the stronger they're sometimes brittle, and is softer but more ductility. How to optimize this? We did some work, but I personally think this may not be able to, how to say, apply in practice. It's very good for scientific research. You can generate very good papers for publication, but for applications, especially try to get ferrite for the end for one component takes a longer time because the cooling rates must be lower, which is decrease productivity. The automotive company may not like it. That's my opinion. And that's why I did not make any effort, even if the project is sponsored by company, but I did not make any effort to commercialize this. That's my opinion. The productivity probably decreased by a factor of 2 or 3.
More? Who?
Yeah, I got one question. I can see that just now in the concluding remarks, you mentioned that originally you tried to plan to set up a group to come up with the testing and test. So I think it's a very important issue. And so you establish standard procedures, data analysis, error sections is come out. Understand. Now, in the end, come up with this consortium or this group to do this. So what is the big issues or bottleneck issues? Not cover. I did not overcome them. Really.
Okay. If you set up the standard, and firstly, you need to make proper procedures first. The testing procedures, specimen design, etc. Draft a document, and you need to organize a consortium, and not only in Europe. For example, a few organizations in China and in Japan, South Korea, America, and Europe, and so on, and at least 10 organizations, laboratories. You send them the same material, describe the test conditions, and then get the data and compare the results. You do not give, for all the organizations, just give numbers, do not give the real name, don't know who is whom. But you just get all the data, process this, and see what's the deviations. If the deviation is too large, and I can't remember the value, if it's too large, you can't have this credit, and this is not suitable for standard, but need to be modified somehow. But if within a certain range, and could be okay. Previously, we do high temperature fatigue test for 26 laboratories in the world, 26 laboratories. They all says we are one of the best, but laboratories in the world. At the end, we get data, the error is a 1,200% difference. Therefore, we cannot create the standards because of which data you believe, all follow the same procedures, same material, same test condition, but use their specimen designs and so on. But use the same specimen designs, the error is 300%, but still too big. Okay, and depending on different kind of applications, you need to convince the committee and what kind of error you can define for these kind of applications. I believe for hot stamping, for flow stress, we believe need to be controlled within about 15% of flow stress. Otherwise, it's too big. Need to discuss with them, let people commonly accept this kind of error.
I just got one more question.
Okay, thank you. I try to answer.
Very quiet. Now, based on your diagram, it's cooled down, and it's all multi-acidic structure.
Yes.
Now, for the safety of the car, you now tweak linear welding or spot welding. Now, according to this welding, you generate heat. Now, in your multi-acidic structure, two multi-acidic weld together, cause problems. How is this solved in the industry?
Okay. It's a very, very difficult problem for this. And that's why for hot stamping of a boron steel, for example, you get martensite at the end for the components, which is very difficult to join join with other components. If you're welding and the martensite may be cracked and occurs, it's extremely difficult. But currently, people, what they use, one is use adhesive bonding for this connected to the other components. Then they use designs in a certain kind of ways to just attach there and to consider about the force in the impact. For example, B-pillars and between the front and the back doors in the middle that we call it B-pillar. That's how to attach it to the bottom, how to attach it to the top. When the impact occurs, they analyze the force, try to avoid welding. Because welding is too difficult for this ultra high strength material, martensite, very difficult. Yes, and if somebody can solve the problem, that would be huge impact to industry. Yeah, this is good. Yes, very practical, very difficult. But if anybody have got solutions, that would be excellent.
Think about this.
Depend on young people.
So your expensive car is just glued together.
Glued together, yes.
It's not so safe.
Yeah, if you look at our laboratory, it's a lot of glued parts.
Okay.
I have one more question.
Yes, please.
Actually, this question is related to question. Weight reduction. And remember, I have been driving a light car for about 9 years on Asia. I don't need to mention the brand. I got feeling that it's too light when I drive about Celsius 90. It's floating, floating. After I change to Europe, the feeling is totally different, very comfortable. So in this way, I always have a doubt on the light reduction. I like weight. Okay. So you really come down the kind of light and not so heavy. The ability, as I mentioned, is really an issue. As a driver, very special for little bit bump low. And so, but from design perspective, we can change some design and then in such a way to make the car more stable and speed higher.
Yeah. Okay. Yeah. Thank you for the question. Lightweight and it's how to say this. This is related to aerodynamics, fluid mechanics. It's not my subject area, but I know many people work on car designs and so on, especially Formula Ones. They can drive very high speed, but light. And normally, you drive within about 100 miles, 100 kilometers per hour within this. You cannot consider too much about aerodynamics. It's fundamental. If you drive too fast, you said it's a light drive about 150 kilometers per hour, so on. You found it's floating. But this is related to the car design. And currently, they design the car. Some car you can see at the back is similar kind of design. Change the drag force in the front with different kind of designs. But if you drive faster, the car is supposed on the to get high pressure on the road. Yeah, that's what they try to achieve. And instead of according to the body weight, they try to use the air pressure to catch the car on the road. That's for the racing cars designs. But for my car, and when I drive about 50 kilometers per hour, I think it's a float because it's not even 2 tons. And I think it's not very. But it's a hybrid electric plug-in electricity.
I just noticed in your graph, just 1.5 millimeter thick steel. That's for the bonnet, other critical parts, 0.8. So 1.8 1.5 millimeter is mainly for the stress, D-frame and pillars.
Yes. For boring steel, initially developed for safety critical components, and safety for bumpers, front and end, and A pillar, B pillar, C pillars, and door impact beams. If there is the impact on the door, side impact is very dangerous because you close to the door, and they put a pillar there. Normally, 20 years ago, I worked with a company in Japanese company that used 2 millimeter thickness. When they worked with us, they changed to boring steel, then reduced 1.5 millimeters. In that way, they reduced weight. But still need the stiffness protect people inside. We call it a safety critical component.
Okay, thumbs up, right? Good timing, 3:50. Thank you very much indeed. And, we should give a round of applause to Professor Lin. Give us a fantastic talk and a lot of good answers to good questions. Thank you.
Just to express our appreciation to your lecture, we met this Prague. Thank everyone for participating in today's lecture, whether you're online or on-site. And also thank you for your question. And I think your contribution is very important for this lecture. So this lecture is adjourned. Thank you.